planetary circulation. Well, hello, Geography 212 class. This is going to be part 2 of Chapter 9. Remember, the first part was about atmospheric circulation. In the second part of this Chapter 9, we're going to take a look at monsoonal circulation, jet streams, and then El Nino, La Nina, and a couple other of these different circulation patterns. So let's get started with monsoon circulation. All that term monsoon means is a seasonal reversal of the prevailing wind direction, okay? And the first bullet down suggests that it results in wet summers and relatively dry winters. That's generally true, okay? That's generally true. Now, we have a very distinct monsoon over Asia, one in India in particular. We also have a monsoon down here in the southwest. It's quite a bit different from the one in Asia. So let's take a look at those. All right, let's take a look first at the monsoon in India. What you're looking at here in the top slide here, this would be during a North American summer. This dark line is really the intertropical convergence zone. Remember, we talked in the first part of this chapter about how the ITCZ moves north during our summer, and that's what it's done. But what lays right there underneath the ITCZ? The Himalayan mountains. So imagine this sort of long, skinny trail of clouds, moist clouds, slamming into the Himalayas, the highest mountains on the planet. So we're getting an incredible amount of orographic lift combining with the intertropical convergence zone. That's why it's so wet here in the summer, okay? So the ITCZ then moves north, slams into the Himalayan and the Karakoram mountains, and produces a great deal of snow at high altitude and a great deal of rain at lower altitude. Then we move down to B. The intertropical convergence zone has moved south, and so the prevailing wind is off the very dry interior of Asia, and those winds blow across that area, producing little to no precipitation. So just make sure you understand then that the Indian monsoon is a result of the intertropical convergence zone moving north and being lifted into the Himalayas and producing a great deal of precipitation. The monsoon in the southwestern part of the United States, the part we get here in Arizona, well, it's really part of a larger monsoon, and I'll do a case study on this a little later, not this week though. It's called the North American Monsoon System. And it really starts down in central and southern Mexico in late April and gradually works its way to the north. And we really start feeling its effects by about July. Look at Tucson, Arizona. This is a bar graph of Tucson, Arizona's rainfall. And you can see you're starting to get the spike in July. And we generally say it begins in early to mid-July in southern Arizona, a little later in northern Arizona. And then look at all that precipitation they get sorry, that was June. In July here, in August, and into September, and even a little in October. And then very dry during the spring and the fall generally. All right. What happens here? What is the North American monsoon system all about? What it's all about is, if you look here, by about July in Arizona at any rate, the ground is at its highest surface temperature. Now imagine very warm ground is heating the air above it. That air is forced to rise. So all through this part of Arizona, we're getting a rising plume of air. Okay, now what that causes is low pressure on the surface, right? Anytime we lift the atmosphere, we're creating lower pressure on the surface. What that creates is right about the border here between California and Arizona, we get what's called a thermal low develops. That's a low pressure system because of hot ground lifting the air above it. Thermal, heat, a low formed by hot ground basically. And like any low, it's going to have counterclockwise circulation. When it sits in this area right here and produces counterclockwise circulation that can bring air in from the Gulf of California, it's a very warm piece of water here, it's very humid above that. And if it can move that air over Arizona into that rising plume of air, it's going to create a lot of cumulonimbus clouds and storms. That's the monsoon. Now, another added feature that helps get this monsoon going, if we can shift high pressure, say, over here to New Mexico, that's clockwise circulation. Look what that's going to do. That's going to pull air also off of the Gulf of California. So if we can pull moist air into this rising plume of air that starts by about mid-July in northern Arizona, we can get cumulonimbus clouds developing and get showers developing. Now, this is very spotty precipitation. One location can get dumped on, can get a half an inch of rain. 5 miles away, nothing. Okay, that's the nature of this Arizona or the North American monsoon system type of monsoon. Anyway, the map you're looking at here is a water vapor image, as you can see. Water vapor is invisible to the human eye. All right, so what you're seeing is a great deal of water vapor here over the Gulf of California, and look at how a lot of that is advecting into Arizona. So these conditions here on this map, and this would have been August 29th, so it's late in August, back in the year 2008. These are very good conditions and set up for cumulonimbus clouds to develop and thunderstorms to develop over Arizona. Now, by the time we get into September, the ground starts cooling off. We start losing the thermal plume, and that's generally when our monsoon season is over. But the monsoon season down in central Mexico generally lasts from about late April into early October. They get a much longer season. So think of the North American monsoon system, or if you want to call it the Southwest monsoon, really moves up from Mexico, and then it moves back down to Mexico. So we don't get it nearly as long. All right, upper air. I'd mentioned a little bit of this before in the first part. If you consider the upper airflow across our latitudes in the United States, we can distinguish between two different types of flow. All right, this first one is you're generally getting air moving from west to east, pretty much straight across the United States. When you see conditions like this in the upper air, we call this zonal flow. Okay, it's going to be pretty stable weather. Not a lot of storm activity going on when we see zonal flow. But look at this. When we get these big waves in the westerlies, we get an excursion, say, down to the south and then back to the north. It can allow very cold air and low pressure troughs to develop. When that happens, it's going to be stormy, cold weather. When we see upper airflow like this, we refer to it as meridional. The reason it's referred to as meridional is these north-south lines of longitude are also called meridian lines. So meridional flow then is when we get these big loops going north and south, almost paralleling the meridians or lines of longitude. Meridional flow. That's going to bring stormy, cold weather. There's no regularity to the shift. We'll see it on and off during the wintertime. Now, sometimes this meridional flow can get pretty extreme, as you can see in this depiction here, where this would have been meridional flow, and it gets cut off from the main flow, this zonal flow up here. And when it gets cut off, these systems can persist in one area for quite a long time. And in some cases, we call blocking systems. So, for example, this would be a high pressure system that's kind of cut off from the zonal flow to the north. It can stay put for a long time. This can have extreme ramifications in our weather patterns. Take a look. Here's a couple of examples. Let's say we get a big high pressure system that sets up, and this is what happened in the summer of 1988. Set up, it's cut off from the zonal flow to the north. It just stayed there. So it's a blocking high pressure system. Did not allow any storms to come across the central part of the United States. They got blocked and sent up to the north through Canada. So that resulted in extremely dry conditions, drought conditions for the central part of the United States. This is another system that happened back in 1993 that sent record rainfalls up into this green area, places like Iowa and Illinois. Again, a blocking, these systems stayed put. This high pressure system just kept pumping all of this moist air off of the Gulf of Mexico into the upper Midwest. And Mississippi River had a very large flood that year. So blocking systems from waves in the westerlies, these can create some extreme weather. This can create extreme weather in the United States. Okay, now here's a very important aspect. Jet streams. And let me just give you a little background on jet streams. Jet streams were not discovered till around World War II in the United States. Some of you might understand the United States got involved in World War II in the 1940s, and one of our major contributions to the war was building and bringing aircraft over to Europe. We built a lot of twin-engine and four-engine aircraft, B-17s, B-24s, B-25s, built them in the United States, and they had to be flown across the Atlantic Ocean over to Europe. What we discovered were some of these flights were arriving hours ahead of what the projected time was. And it turns out they had, unbeknownst to the pilots, got themselves up into these jet streams, which you can see what the words here, these swiftly flowing air currents that can get up to speeds of about 200 miles per hour. Okay, so what are these things? All right. Well, there's a couple that are very important to weather in the United States. We'll start here with the first one, and I would argue this one is the most important one. So please, remember this one, the polar front jet stream. Well, the polar front jet stream is going to flow at the top of the troposphere, at the tropopause, exactly at the boundary between our very cold Arctic air, continental polar air, and the warmer air. Could be MP, could be MT, could be CT air to the south. Okay, so remember, the different air masses of different temperature and moisture don't mix, fronts set up, and in the case of the polar air to the north, warmer air to the south, we get a polar front jet stream that sets up. Now here's just a visual depiction of it. You can see that blue is going to be the very cold air, and the red color is the very warm air. Look where the polar front jet stream flows, right at the boundary between those two different air masses and up at the top of the troposphere. So top of the troposphere at that boundary. They're pretty narrow. These picture them like tubes of air that flow very swiftly from west to east. Here is a cross-sectional view of where the polar front jet operates. Now, if you go back to the equator here, intertropical convergence zone, lifting air, okay? Hadley cell carries this air to the about 30 degrees north, and where it descends, we get another one of these jet streams. It's called the subtropical jet stream. Same thing, swiftly flowing air at the top of the troposphere, but this one is going to happen right where the air descends at around 30 degrees north. Now, obviously, they're going to shift back and forth with the year. Now, here's the polar front jet. You can see it occurs at the top of the troposphere, right at the boundary between this cold air to the north, the warmer air to the south. So that's where they're located, the polar front jet and the subtropical jet. That's where they're both located in a cross-sectional view. Now remember, I had mentioned earlier in the first part of chapter 9 here that all of these things shift north and south with the seasons. Everything shifts to the north during our summer, and everything shifts to the south in our winter. So the polar front jet stream does, okay? Summer jet stream, polar front jet, would be far to the north, mostly in Canada, but you can see sometimes that winter jet, this could be either the polar front or the subtropical jet, could be down as far south as across the south. Okay, so just remember, this is just, everything shifts north and south in the summer and in the winter. So subtropical jet, as you saw earlier from the depiction, it's found on what we call the poleward or northward side of the Hadley cells, and it's strongest in our winter. We can sometimes see that thing appearing in our wintertime, and it's less variable with latitude than the polar front jet stream. In other words, it tends to stay at about the same latitude, where the polar front jet stream is going to be wherever the polar front is, and that can be extremely variable. We do have other jet streams. Just for your information, we have a tropical easterly jet. You can see this occurs over North Africa for the most part. We have one that's relatively new discovered, the low-level jet stream, that's occurring only a few hundred meters above Earth's surface in the Mississippi River Valley. And this is not well understood. There's a lot of research going on to this. But this low-level jet stream can feed into a lot of thunderstorms that can develop in the Midwestern part of the U.S. in the summer. So there's a lot of interest in that particular one, the low-level jet. All right. Now we're going to talk about El Nino, La Nina, and the Southern Oscillation. I'm sure you've heard about this. Now, if you could, to set this map up, this is South America and North America, these brown areas here. And normal conditions are, remember when we talked about the intertropical convergence zone, how just north of the equator, the wind blows from the east. All right, it's an easterly wind, so it would typically blow from the east. So normal conditions then are going to blow this warm surface water over to Indonesia and the Philippines. That's what this red is, the warmest water. So normally then we get the warmest water over here on the western side of the Pacific Ocean. Okay, we'll talk about that in a second. What does that cause over here? Well, if you're blowing warm water off the surface over here, you're going to get upwelling cold water. So typically, we have very cold water off the coast of South America and Central America here under normal conditions. Now, cold water going to produce dry conditions. Cold water doesn't allow much evaporation, so there's very little humidity in the atmosphere, dry conditions. Go over here to the Philippines, though. Very warm surface water is going to allow a lot of condensation. It's going to allow a lot of cumulonimbus clouds to develop, a lot of precipitation. So then normally it's wet over in the Western Pacific in Indonesia and the Philippines, and very dry over here. Let's switch to this. I'll talk more about that last slide in a second here. El Nino conditions, however. El Nino conditions, for some reason, this easterly wind reverses itself. And it now is a wind, it's a westerly wind that takes this warm water and it moves it over across the Pacific Ocean, and in extreme El Nino scenarios can pile up along South America, and this warm water will flow all the way up the coast of North America. Now, let me give you a little history on this. Back in the 70s, Peruvian fishermen were out here, and like I say, normally it's cold water, cold upwelling water brings a lot of plankton up and there's a lot of food for fish. This is one of the world's richest anchovy fisheries off of Peru here. And so they're out there fishing in December, and first of all, they felt the water was warm and there were no anchovies. This was very unusual. I don't think they'd seen that before. And so because this warm water arrived around Christmas time, they called it El Nino. When you capitalize the N in Nino, that would typically mean boy. El Nino means the boy. But capitalize the N, it really stands for the Christ child. So because this water arrived around Christmas time, they referred to it as the Christ child or El Nino, and that name is more or less stuck, okay? So El Nino means the arrival of warm water around Christmas time or sometime in the winter. All right, anyhow, let's get back to what happens as a result of that. Now we're moving the warm water over here to the Americas. Now we're going to start creating a lot of evaporation, a lot of cloud, a lot of precip, and that will typically move across the southern United States. Last winter, those of you that were listening to the press or whatever else probably heard we had one of the strongest El Nino conditions ever recorded on the planet. Well, we did, and it was forecast to be a very wet winter, wet and snowy winter across the southern United States, including the Southwest here. Well, it started off that way. We had very wet and snowy December, and by early January, maybe mid-January, it stopped. And then we hardly had any more precipitation. As a matter of fact, had record high temperatures in the Southwest in February last year. But just north of here, from Northern California on, they did get excessive amounts of precipitation. So we don't always get exactly what we think we're going to get, even though we had this very warm water situation last winter. Now, the other thing you see here is this term southern oscillation. Climatologists didn't really think that the term El Nino was really very descriptive of a meteorological application. So what's happened now is we call this phenomenon El Nino Southern Oscillation. That gives you the acronym ENSO, ENSO, and that's typically how we refer to this situation now as ENSO. You don't hear about El Nino quite as much, okay? Now, what's La Nina? Let me see if there's a slide here for La Nina. La Nina is basically normal conditions, all right, only more intense. So, normally La Nina is showing the normal direction from the east, piling up warm water, but the winds are stronger than usual. So what happens is you get even more warm water piled up over here. They get an increase in precipitation in the Philippines. Meanwhile, over here in the Eastern Pacific, where we are, you're getting more cold upwelling than usual. The water is colder than normal. So that's what happens during a La Nina event. Now, La Nina events, now let's see where I put that. I think just pardon me for one moment. I guess I didn't put it in there. All right. Anyway, so let's just summarize that up, and then I'll talk a little bit more about it. Normal conditions. The easterly winds blowing sea surface water over toward the Philippines. Warm water produces a lot of convection, a lot of showers and thunderstorms. Meanwhile, over here, cold water upwells normally, and it's dry conditions. We go to El Nino. Remember, El Nino is a reversal of the normal conditions, brings the warm water over. We get the rainfall over here. And then finally, La Nina is normal, but even stronger. So it's a more extreme condition. So more rain than usual here, drier and colder than over here. One way to think of El Nino and La Nina, at least for the Americas, is that an El Nino event is a warm water event for us. A La Nina event is a cold water event for us. So it's a good way to think of it, I think. Now, this is an interesting graphic to take a look at. This is taking a look at the frequency of El Nino and La Nina events starting in 1950 up to about 2011 or so, up until a few years ago. So what I want you to take a look at first here is look at from 1950 to 1975. It's pretty clear that the Pacific was dominated by La Nina or cold water events. As a matter of fact, by the time we get into the early 1970s, many climatologists were predicting that the planet was going toward an ice age. We saw planet cooling. We saw a cooling event taking place into the 1970s. And like I say, we were dominated by La Nina events. But things really turned around just after the mid-70s into the late 70s and on. If we look at the late 70s and on to nearly current conditions or to current time, look at this. We see a total dominance of El Nino events. You know, the big question a lot of people have, a lot of climatologists have, is this dominance of El Nino events since the late 70s a result of global warming? Well, you know, there's a correlation. In other words, the two events occur together, but is one causing the other one? Jury's out on that one right now. But at any rate, you can see that we've had some very strong El Ninos. That one there in 1983 was the strongest one ever recorded. We had another big one here in 1998, and then 2015 was a big one that doesn't show up on this map. Now, let me talk about this over here. How we rate El Ninos and La Ninas is their departure from normal of temperature in Celsius. And what temperature? We have many buoys. Check it out right here. We have many buoys out in the Pacific Ocean that are constantly measuring sea surface temperatures. And this is how we know if the water is warming up or cooling down. Where's that warm water sloshing back and forth? These buoys will tell us that. Now, if we go back to this chart here, if the sea surface temperature gets to be, say, in this case, 1 or to 1.5, let's call it 1 degree Celsius above normal, we call it a mild El Nino event. If we get to be, say, 2 degrees Celsius above normal sea surface temperature, we call that basically a moderate El Nino. Once we hit 3 or higher, we now have a major El Nino event occurring, and there's been 3. There's been 1983, 1996, and then 2015. All were about 3 degrees Celsius above normal. And then we do the same for La Nina events. Okay, 1 degree, 2 degrees below normal will tell you if it's a moderate or a strong La Nina event. Okay, so as we saw the buoys. We've got a lot of these buoys out there now tracking the temperature of these oceans. Now, El Nino, La Nina is not the only one of these oscillations cycles that we have, and I'm going to show you briefly a few of the other ones. The North Atlantic oscillation, or NAO. We really, if you look down at these first 2 bullets, we have what's called a positive index and a negative index. That's how we rate these. So you can see the positive index means we're going to get stronger than usual winter winds blowing across the North Atlantic. What does this mean for Eastern Canada and the States? colder winters. So we're very interested in when we see these things happening. The negative index means a mild winter, for example, in eastern Canada and the United States. And I can't really give you the cycle on these because you see the last bullet, they're not regular. They don't really happen that often. We don't really know exactly what the cycle time is on these. All right, Arctic oscillation. We have an Arctic oscillation. This would be on the Arctic Ocean. Okay, we have a positive phase and a negative phase. Positive phase is going to give us, say, mild weather in the United States. The negative phase is going to give us a colder winter. So that can affect us, the Arctic oscillation. And finally, we have this thing called the Pacific Decadal oscillation. Okay, we have a warm phase and a cold phase here. You can see during a warm phase, we can have a dry, mild winter here. But when we get cold phase, we can have a cold, wet winter. Phases shift every 23 years. In other words, these conditions can stay in effect for years at a time. It's not like a La Nina or El Nino that really only lasts a year or less. These Pacific Decadal oscillation can maintain this type of temperature in the ocean for many years. And you can see these phases can shift maybe every 20 to 30 years. When you look at this particular graphic here, you can see that we do have about a 20 or 30 year shift back and forth. We start back in the 1920s, go back in here, we can see there was a relatively warm phase of Pacific Decadal. But then we go late 40s into the mid 70s, we have a cold phase of the Pacific Decadal, back into a warm one, and then we've been really pretty quickly back and forth from about 2000. All I could say about these sorts of things here is that, the more we learn, we really do not know. The jury's still out on these things, and there's going to be other of these cycles and oscillations that we simply haven't discovered yet. It's all very fascinating. It all very much does contribute to the weather that we get from them. Okay, so that's it then for Chapter 9. A lot of information in there, so please go back and take a good read of that. Okay, that's it for now.